My name is Katherine Davis. I'm a postdoc in the lab of Jay Groves at Princeton University and a member of the Arnold O. Beckman Postdoctoral Fellows Class of 2015. Through this video, I hope to convey the impact that the Arnold and Mabel Beckman Foundation has had on my career and walk you through my scientific proposal and the progress I've made during my tenure as a postdoctoral fellow. My project was broadly titled Directing Metalloenzyme Movies. Enzymes are tiny molecular machines which facilitate chemical reactions in living things. Some of these reactions are so complex that chemists have yet to recreate them synthetically. This is particularly true for enzymes that incorporate metals. Understanding how these so-called metalloenzymes function is critical for advancements in human health and medicine, as they are not only integral for the natural production of drugs, like antibiotics and antiviral molecules, but they can also be manipulated for the treatment of diseases more broadly, like cancers and neurodegenerative conditions. One approach to study metalloenzymes is via the use of X-ray techniques like crystallography. The development of X-ray methods over the past century has allowed scientists to determine the three-dimensional structures of these large biomolecules, as well as probe the metal centers directly involved in catalyzing their associated reactions. Unfortunately, due to the rapid pace of metalloenzyme reactivity, it has historically been difficult to gain insights into their dynamics. Enzymes are flexible, and movement is critical to their respective functions. While static snapshots are invaluable, we often don't know how these systems change over time. Proposing a mechanism based on pre- and post-reaction behavior is a little like being asked to write a book synopsis after having read only the first and last page. The goal of my project was to develop and apply new tools to visualize the dynamics of iron-containing enzymes using X-ray crystallography. I'll give an overview here of two different methods I employed. The first project involved crystallization of a metalloenzyme named SWEB, involved in the synthesis of a unique signaling molecule that bacteria inside our bodies use to communicate with each other. Such experiments are particularly complicated in enzymes like SWEB, since they contain clusters of iron and sulfur, which are highly sensitive to oxygen and damage easily. To avoid this, our experiments had to be performed in a special chamber, isolated from the atmosphere. Biochemical analysis had previously suggested that SWEB contained three unique structural domains: one, where the chemistry occurs; a second, proposed to mainly interact with the input molecule; and a third, whose functional assignment is largely speculative. However, an enzyme containing these three domains together had never been visualized. We hoped to not only investigate how the signaling molecule was generated, but further elucidate the functions and interplay of these different domains by trapping the enzyme in different states within our crystals. There are two main methods to do this. Either we must form a stable intermediate to crystallize, or we have to start the reaction in a crystal which has already formed. Because enzymes are so dynamic, the second approach often results in degradation of the crystals due to the motion of the molecules that form it. Instead, we withheld a critical component of the reaction that would cause the enzyme to stall out mid-cycle and thus create a stable state that we could then crystallize. Our results were surprising. The domain believed to interact with our input molecule barely made any contact at all, while the input molecule itself formed its own stable structure deep inside the enzyme. We were able to identify a short segment of the enzyme connecting the two other domains that provides key interactions with the input molecule to position it for the ultimate reaction. Previously overlooked due to its size, this small section may hold the key to understanding how similar reactions occur in enzymes known to produce complex antibiotics. The second project, by contrast, focused on an enzyme called Tau-D, which contains only a single iron atom and is involved in the bacterial acquisition of nutrients from the environment. Although Tau-D is the most well-characterized in its class, this extensive characterization is exactly what makes it the ideal candidate for testing a new method to visualize structural intermediates. Like SWEB, it's a member of an enormous class of enzymes known for their involvement in the production of clinical antibiotics. We know a lot about the mechanism of Tau-D. We can even describe the short-lived reactive complex responsible for initiating its chemical reaction. What we don't know is how other similar enzymes with the same short-lived intermediate state avoid catalyzing the same chemistry and instead perform different reactions. Preliminary studies suggest that the orientation of the reactive metal species may play a key role in determining the outcome of a reaction. To prove such a theory, however, we must be able to visualize the intermediate in 3 dimensions. Both the nature of the reaction and its speed limit our ability to use the methods proposed for SWE-B. Instead, new biochemical work indicated we might be able to create a suitable structural mimic of the short-lived intermediate by substituting in a different metal capable of maintaining a more stable complex. Indeed, by employing such an approach, we obtained high-quality crystals that led to the first ever visualization of this key reactive complex in any member of the enzyme family. Our results confirm the utility of this method to obtain structures of the key short-lived intermediate and provide further evidence to support the hypothesis that different metal species orientations facilitate different reactions. There's still a lot of work to be done, but these experiments provide a flipbook-like framework to which we can add pages, or frames, allowing us to piece together a fuller story. In the spirit of Dr. Arnold O. Beckman, it is my hope that the development of new methodologies like these for the study of metalloenzyme reaction intermediates may one day transform the study of chemistry and its applications to human health. Dr. Beckman's legacy reaches far beyond his revolutionary innovations like the pH meter and the oxygen sensors installed in the incubators of premature babies. Together with his wife Mabel, Dr. Beckman created a legacy of philanthropy that continues to support forward-looking scientific research that nurtures the young minds who will eventually lead it. I am profoundly fortunate to have benefited from their foresight and generosity. The Arnold O. Beckman Postdoctoral Fellowship has allowed me to expand my biochemical repertoire and develop a truly interdisciplinary skill set, preparing me well for the next steps of my career in academia.